Hello everyone, and welcome to another episode of Solving Advent of Code in Rust, and try to learn some Rust in between. I'm Eugene.
Luciano, hello.
Roberto.
Thank you everyone for following along. If you never did Advent of Code, it's basically a coding challenge that's published every year around the Christmas period, and we're basically working on last ones. We have an exercise every day up to the 24th of December. There are 24 challenges. You can find them on adventofcode.com. We're publishing our code on GitHub. If you have a banner for me, Luciano, please. Perfect. Thank you very much. So we publish this on GitHub. We have a YouTube channel as well, where we publish all the recordings of this. You can find the recording of this on the Twitch channel description. And if you're watching this on YouTube, we are also streaming this every Monday. You can find the link to the Twitch channel on the YouTube description. So in the last episode, we finished off something, and we're going to start a new exercise today, which I think Luciano is going to drive.
Sure. So let me add my screen. Is it readable enough? What do you think?
I would zoom in one more click just to be sure.
Let me do that.
Yeah, perfect.
Okay, so let's see. So I'm not going to read all of this, to be honest. I already had a look at the assignment, so I think I can summarize the idea a little bit. So basically, this is, we need to write something that can evaluate expressions, something like this. So we read this as a string, and we need to basically provide the solution of this expression. There is only one caveat, is that the math doesn't really work, as we know. There is a little difference, which is there is no real operator precedence, because we know in real life multiplication comes before addition. Here, the only order is the order of when you actually see the operand, right? The operator. So if you see a plus, you apply immediately the plus. Doesn't matter if you have a multiplication afterwards. And you can use parentheses if you really want to enforce priorities. Of course, if you get parentheses here, that will need to happen before the addition. I hope that makes sense, that I am explaining it correctly, but I think we can look at this example to explain what's happening. Actually, let's look at this one first, because here we don't have any parentheses. So basically, we apply all the operators in the order we find them. So for instance, here, this is the first operation we see. We immediately apply that, and we get 3. Then we get 3 multiplied by 3, and we get 9. Then we get 9 added 4, we get 13, and so on until we get to the last number. And this is the result. If you get parentheses, of course, you need to give priority to the parentheses. So for instance, here, you don't do 1 plus 2, but you need to do 2 multiplied 3 first, and then you can do 1 plus 6, and so on until you resolve the entire expression. Now, if we look at the input, these are a bunch of expressions that we need to solve, and there are like hundreds of them. 371 of them. And the result, so what we need to return to solve our challenge is, for every single line, we calculate the expression, we evaluate the expression, we get one number, and then we sum all these numbers to get one final number, which is going to be the solution to our challenge. Does that make sense?
Does
Any additional comment?
That's some. And we got a suggestion in the chat.
The tricky part is handling the parentheses in the end.
That's it. I really wish we had like an eval in Rust, and then it's like line eval.sum.
Yeah, but you are cheating. And
but it won't work, because it would do the correct order of operations.
Fair enough. And I'm honestly suspecting that the guy that came up with this challenge basically thought of that tricky mathematical rule just to avoid people to use the default eval, for instance, in Python or in JavaScript. Right?
Yeah, probably, yeah. Or maybe just had enough conversations with people who do not know the order of operations. So they went, hey, let's do a challenge around this.
Yeah, exactly. So I have in mind a solution that I might try to explain with a sketch, and this is something new for us. We never really done sketching things, so let me try to share my other screen. So window, there you go. Okay, you should see like a drawing board. So I'm going to try to explain an idea for an algorithm that we could use to implement this. And then if you think it makes sense, we'll try to implement it. So as an example, we can do, I don't know, 1 plus 2 multiplied 3 plus, I don't know, 4. So my current idea is that this is going to be, of course, a string, and we have a sequence of characters that we can iterate through from left to the right.
Also, a small note, all the numbers in our input are numbers with one figure.
Actually,
no two figures number.
Yeah, single digit, all of them. No spaces
always
either.
A single digit.
Or were there spaces?
There are spaces,
but we don't care about spaces.
We can easily ignore them. Also, I think I noticed, because I already had a look at the input, that there is never a 0 and never a 1. I don't know why. I think it's just to make our life simpler. So we could also assume that numbers will be always between 2 and 9s, the digits of the numbers.
And my question is why? Because 1 is a very legit number, and even 0. But okay, let's not go down that rabbit hole.
Like if we want to be super strict and only implement like a solution that works specifically for this input, we could even ignore 0s and 1. But yeah, it doesn't matter that much.
Also wanted to say thank you, MXKW, for following.
Thank you.
Just a little shout out.
So the first idea, I'm going to explain it without parentheses, and then we can see how to include parentheses with recursion and make it more generic. But the idea is that we can have an accumulator, I'm going to call ACC now, and a current operation. And by default, just as a starting point, our accumulator might be 0 and our operation might be a plus. And the idea is that every time we go through characters, we can find either a number, either a space, or an operation, like a plus or a multiplication. Again, let's exclude parentheses for now. So if we find a number, then it means that we found something we can start to accumulate. So for instance, we start from this position, and we say, okay, there is a 1, so this is a number, we can accumulate that number, which basically means we take the number, we apply the current operation with the current accumulator and the current number. So that basically means 0 plus 1, and that gives us 1. And at that point, that becomes the new value of our accumulator. So at this point, we will remove 0 and we will get a 1. Then what we do, we keep going and we find an operator. And that means we need to replace the current operator. And in this case, we replace a plus with a plus. So it doesn't make a lot of difference, but let's do it. Then we find another number, this 2. And at that point, we need to accumulate that number. So now we do 1 plus 2, and the new number becomes 3. And basically, we keep going. We find a new operator. This becomes a multiplication. Then we find 3, and we need to apply the 3. So we do 3 multiplied by 3, and this gives us 9. And then we keep going. We find a plus. We keep going, and we find 4. So we need to do 9 plus 4, and we get 13. And this is the solution of our operation. So this is the end. Does that make sense?
Yes.
So that basically allows us to linearly go through the input and keep evaluating on the fly. Like as we find something to accumulate, we just do it on the fly.
Yeah, and memory-wise, you just have an accumulator and an operator that are
exactly. So we are not allocating anything except these 2 variables. Okay, now let's make this a little bit more complicated. And let's, I'm going to repeat this. So let's do 1 plus 2 plus, multiplied 3 plus 4. And let's put some parentheses here just to have an example. Now, we can do exactly the same algorithm. The only difference is that when we find an open parenthesis, it's kind of the beginning of a recursion. So we will have again an accumulator and a current operator. And then basically we start and do the same. So initially it will be 0 and plus, then 1 and plus, actually, we get to the point where we have 1, we find another plus, and then we find the open parenthesis. The moment where we find an open parenthesis, what we need to do is to find the matching bracket for that parenthesis or the closing parenthesis. So at that point, we start to do a scan until we find the equivalent closing parenthesis. This might be a little bit tricky because if you have other open parentheses inside, you need to make sure you are counting them so that you are finding the one that is closing the first parenthesis you found. And at that point, we have a substring like this, and we can essentially call recursively our function with this substring, saying, please evaluate this for me. And then the results that we have is something that we can accumulate. So if we recursively evaluate all of this, we know we are going to get 6. So basically, we assume that all of this is already value 6. And we keep doing the same algorithm over and over. Of course, if you have nested parentheses, you will do recursive call and then keep recursing until you resolve all the levels of parentheses. So we have a question, which is saying from Tommaso. So make a recursion when you find a open parenthesis, stop to read the string. Okay, and you basically try to find the matching parenthesis, yeah.
And then we go on until the end of the string. When we run out of character, in theory, the accumulator is our solution.
Exactly, yeah. So
I guess...
I hope that...
Go ahead, Luciano, sorry.
No, I was asking if that makes sense, we can just switch to the code, but feel free to ask.
I was going to suggest or ask for finding the closing parentheses. If we pass recursively a substring, which is going to initialize an accumulator and operator, it might be simple enough to find the matching one if we just start from the back, basically. Although there are options where you could have like 2 open ones, I suppose.
Yeah, exactly. So that just to make an example, you might have 1 plus 2 multiplied 3 plus 4 plus 6, let's say, and you might have, I don't know, parentheses here, but also, I don't know, parentheses here. And you might also have here, I don't know, multiplied 7 and other parentheses here, for instance. So you need to do the counting to check, for instance, that this one is matched by this one, and this one is matched by this one, and so on.
Tommaso actually has a very good comment there. He says we don't need to find the matching parentheses, actually, because when you find an open parenthesis, you just need to start another process, which ends when it finds a closing bracket.
That is not completely true, because you have to count. Because if you start with the first parenthesis here, you stop with the one after the 4. But it's not his closing parenthesis.
No, but if you do it recursively and you just start a new process when a new one starts, basically you have one of these function scopes at the 1 plus thing. You start a new one when you find the parentheses, and you have 2
but I don't
times
think we are changing
you start
the
a new one when you find the open one.
Yeah, but we are not altering the string. We are
well, we're passing substrings, though, right?
Yeah, we are passing a substring, but that is not altering the
string. But you're not... well, if we also remove the substring from the current instance...
if you also remove the substring from the original string and we put the result in, yeah, that's true. But we are not touching the string. We are just slicing it. But slicing it in Rust is just a matter of pointers.
Yeah, you have like a
copy of the string. You are doing way less operation in memory. If you start to change the string because you put in the place of parentheses the result of the parentheses and so on, you are altering the string, and is more time consuming. Instead, how Luciano described it is just integers counting stuff. So
yeah, just to make it more obvious where this one that needs to match, I don't know, this one and this one.
Yeah, but how do we find them was the question, basically. Like, how do you find the matching bracket?
That's like a sub-problem in the problem, but it's not that hard. Like, one way that I know is that basically you can start a counter, and the first time you find an open bracket, you increase the counter.
Fair enough.
Then every time you find a closing bracket, you decrease the counter. And essentially, the first time you see that the counter is 0, it means you found the matching bracket.
That's fair enough.
Of course, assuming that the syntax is correct.
We are not checking any kind of invalid expressions or stuff like that. We truly believe that the input is right.
Currently, the inputs are correct, but that's the benefit of advent of code. In the real world, this won't be true. Cool. So let's go to code then, right?
Okay. So let me switch window. So stop sharing this and share my editor. All right, so let me put this one on the side so I can type.
You need a better setup.
Yeah, I need a bigger desk for sure. Oh, I'm glad that Tommaso liked the pencil board. Good, we'll keep doing that, hopefully. Okay, so let's start by doing FN eval, I guess, where we receive an S, which is going to be an str, right? And that returns U64, I guess, or let's do an I. No, let's do U64. Oh, not 63.
Do we know if they're going to become
actually, good question. Let's double check the input. I did check already, but there are never negatives. So if we search for a minus, there isn't.
Okay.
And there are no divisions, and there are no ones, and there are no zeros. Just if you are curious, there are 2, 3, 4, 5, 6, 7, 8, 9. And then open parenthesis and close parenthesis. So these are all the symbols we really have in our input file. So I think it's fair to say that this is going to be always a positive.
Yeah, also because the solution is a U64, I think, and then we have to sum them together. So if we don't want to cast forever, let's start wide. And
exactly.
That's fair enough.
What do we do?
You said we start with a mutable accumulator, a mutable operator.
Initially, this is 0. Now we need a way to model operators. I think the easiest thing we can do is just to define an enum. So we say enum operator, and an operator can be either an addition or a multiplication, right?
Okay.
That should be easy enough. And then we can say let mute op, and initially this is going to be operator add, right?
Yes.
Okay, so now we need to go through every single character. And I know that this is a little bit tricky in Rust, right? You know that?
Didn't we have a chars thing?
Let's try. So if we do s.chars,
I think we used it before. Yeah.
Then you lose the index, right? If you just go with
chars. You can do chars enumerate, and you also have the index. The problem is that at one point when we find an open brackets, we have to jump.
Exactly. So it will be easier to do something like for, I don't know,
or even start with a mutable I starting from 0.
s.len, something like that. Sorry, in 0 ... this.
Okay, no, sorry.
So that could be an idea, but then there is a problem. If you do si to get the current character, so let's say let c equal that, this is not going to work because strings in Rust are UTF-8. So you cannot index like by position.
Well, then,
makes sense?
Yeah.
Okay.
I only know this, I'm going to be honest, because I looked it up in advance. And I did spend some time figuring this one out.
There is no concept of rune like in Go?
There is a concept like that, but of course you get like an indexed view in the string that tells you exactly at which byte every character begins. So you could do that with an iterator, and that iterator will give you like an indexed view on the string.
So now on that C that is of a specific type that I don't know, you can't check if it is a 1, if it is a plus. You can't.
No, the problem is that this C doesn't really do what we want to do, I think. Well, let's return 0 here, just to make it happy. Here is the error. it cannot be indexed by usides because
okay.
it doesn't really have fixed size characters, if you want.
Okay, and how can you address a string? You can't.
Tommaso suggested
collect
yeah.
this, which may be a fair solution, to be honest. Maybe it's better than what I initially thought. I'm going to explain what I initially found, and then we can discuss which one to pick.
Okay.
So what I did something like, I don't know, let's call it index, I guess, for now, for lack of better word. And basically what I did is s dot char indices, I think is what I used. And that gives you an iterator that for every element gives you the position and the character. So you get, if you collect all of that, you basically get an indexed view in the in the string.
Okay, and this basically traverses the entire string and transforms it into this other type of data structure.
Yeah, you can use a vectq or whatever, a vector, whatever you want to, that then you can work on.
Okay.
But I think it's not that different from what Tommaso is suggesting, so maybe that's simpler.
Yeah, chars collect probably is allocating a vector of chars, but probably it's simpler to reason on top of it.
So, because this one is allocating anyway. Like if we do collect of this into, I don't know, a vec of char. No, actually it's going to be usides and char, I guess. So this is already getting a little bit more complicated.
No, okay.
Yeah.
Let's go with the chars collect.
Cool. Yep. So let's call it, what do we call it?
Expression.
Charlist expression.
Let's call it expression. By the way, do we want to use a vectq? Because then we can consume it as we read. And essentially our loop is going to be until there is stuff to consume in the vectq.
Okay.
Yeah, that makes sense.
And we pop on left.
Yeah. I think we'll need to import it, vectq of chars at this point. And this is equal to s.chars.collect. And then we'll need to import this guy. Oh, it did it.
Oh, no, it did it automatically. So
automagic.
So now we can do while not expression empty, I guess. Is empty. We can keep going. Okay, now we have this wonderful kind of a state machine where based on the current character, we'll need to figure out what to do. So let's do let's see equal expression dot pop. Oh, now is it front or is it back?
Left is front.
Front.
Okay, let's start with this. And we'll see. We'll write a little test,
Actually,
I guess.
We should probably test it.
Yeah, it's not a very good naming because Arabic culture have the front on the other way, respected to Western cultures. So it's not inclusive.
Yeah, correct.
So left and right are left and right. So even if you don't... So the terminology
I guess, we'll test it and we'll figure it out. So now we need to check. The first thing we need to check if it's a number, right? So if...
Actually,
let's start the way to check. We can do a match. Let's start with if then we can convert.
If we do 0 as a character to 9 as a character, and then we can say includes.
We have to unwrap on line 14.
See. Oh yeah, you're right. We need to unwrap.
Because
and now it's a proper
that expression is empty, so it could be because the while is protecting us from that. But well, Rust is not understanding it. Okay, now if it's a number, we apply the number and the operation, and we put back in the accumulator.
Yes.
So based on what is in op, so if op is a plus, is a sum, is an add.
Yeah,
sorry.
We need to do that now. Yeah, let's do it in line, and then maybe we'll add here some function to do to apply stuff.
You can add the function to an enum.
Actually, let's do it now because I think it's just nicer. So we can do implement enum. Sorry, op, and then we can say fn, let's call it apply, I guess, and left and right, and they are both U64. And this returns a U64. And then basically what we do is match on self. We need also to have reference to self.
Okay.
Of course. Self, and the case where it's op add, basically we want to return left plus right.
Plus right.
And the case where it's op multiply, we want to return left multiply right. I think that will do it. So now what we can do is literally saying accumulator is equal to op apply
okay.
of accumulator and C, but C needs to be a number.
C is a number, yeah.
So let's do let n U64 equal C. Now I don't think we have a parse. It needs to be a string. So what we can do is format. This is a little bit ugly, but whatever. If you have better ideas in the chat,
can we not
let me
do
know.
From char or something like that?
I don't know what is format.
It creates a string basically, and now we can do dot parse dot unwrap, I think.
Chars is for in any case. Sorry, rephrasing. Chars is castable to integer somehow.
But if it is, then we'll need to do.
Less.
You mean like in ASCII code?
Yeah, you have to do minus 48.
Exactly. Okay.
So C as U64 minus
as is ASCII.
The as is not with dot. It's just C as, no, for the casting.
Oh, as U64.
The minus dash.
Let's see if that works.
Okay, let's see if it try to explode.
You can do it. I'm not really sure what do you get, but
try dash remove. Okay, for 48. Yeah, okay, remove a comment line 25.
Let's comment this one, and that should be the same. But this is basically from
48 is the ASCII
code to numeric value.
Yeah, is the ASCII of 48. If you ever wrote in assembler parser for numbers in strings, you do that.
Sounds fun. I don't know what's
or
complaining
you can
here.
Do like
this needs to be mutable.
Like suggestion 0 as U64. So even if you are a BCDIC, it will work. I don't think this will ever run on AS 400 from IBM, but even in that case,
this is the moment where I lose, Roberto. But I believe you.
In line 26, instead of 0, in 48, they are suggesting. Look in the chat.
This one?
Yes. Instead of 48, they are suggesting that one. So that is cross-platform, cross-encoding, cross-region, cross everything. But well,
okay. I mean, we can try if that works.
Yeah.
I mean, it's not that different from what we did here. Actually, we are removing 48.
Instead of doing 48 or coding 48, the suggestion use
use
the comment instead of 48 to not code 48, because 48 is true if you are ASCII. But if you are a BCDIC, that is another table that is used in AS 400 from IBM, you have the numbers are still in sequence, thanks God, but 0 is not 48, it's somewhere else.
But I think they use UTF-8, so it's probably going to be ASCII.
This is super safe.
But whatever. From whatever.
Yeah, for whatever to
the technical term for it. Yeah.
Okay, so at this point we did case 1. The second case is else if. If it's an operator, so C equal this or C equal that, right? At this point, we need to replace the operator. Now here we can do another nice thingy, and we can implement
a new
the from char, I guess.
From char, okay.
From char for op, and basically what we need to do is fn from C as char, and it returns a self. Now what we do is match on C, and then if C is pass, we return op add, and if it's multiply, we return op.
He's complaining in line 17 about something.
And this is reachable, I guess.
I know, it's fine. Okay.
Makes sense?
Tommaso suggested try from.
Oh, to make it failable, which could be, and then we'll need to fail here. Do we want to do that?
In our input, it's not going to happen. So.
We've already made a bunch of assumptions around their input, so I guess.
Yeah, I think we leave it. If we have time at the end, we try to handle the errors and support invalid stuff. But it's a good suggestion anyway. Like try from.
Yeah, we can start to support the numbers with more than one figure and so on. But let's not write a tokenizer, please.
So now what we want to do basically is that op is going to become c dot into. Right?
Just that is enough.
I think so. Does it work? Because op is an operator. C is a char, so I should be able to figure out.
Yeah, okay, cool.
Okay.
Now we have
and of course, if we were using try from, since this will return a result, you will need to do unwrap, but into is like it's never gonna fail, or at least it's gonna panic. So try from is a little bit more defensive because we have an opportunity to handle failure. Okay, now I don't know if we want to ignore parentheses.
I would want to test
just for a second to test if this works.
If you want to write a small test just for this, yeah, okay, let's go.
Basically, here we return accumulator and that's it.
Yeah, let's do a simple one just to make sure all this code that we wrote is working. There's like 40, 50 lines of stuff.
Exactly. So fn test eval. And what we want to do is essentially say assert equal of eval of a string, if I can type today. A string, let's say 2 plus 3 multiplied 9.
It is 45.
Needs to be the same as 2 plus 3 in parentheses. Wait, it's 2 plus 3 in parentheses.
Yeah.
Times
multiplied 9.
Multiplied 9 because the Rust has a precedence of operator.
Complicated math, man.
Okay, let's see if that works. Cool, that works. So we did
the trick of casting the char worked.
Nice, I like it. So let's remove this guy. And also this pop front was the right one.
Yeah, okay, the front is...
Let's add another quick test just to be sure. Let's say, I don't know, plus 44. At that point, that will be just plus 44. Actually, 44 is not going to work because...
No, because it's just casters.
Okay, still working, so reasonably convinced.
Yeah, reasonably confident. Without parentheses, it's working.
Okay, so next step is to start supporting parentheses. So else if c equal open parentheses, then it's where we start to do complicated stuff.
So here you want, let's recap if I understood correctly. Here you want to search for the matching closing parentheses.
For the matching
closing parentheses.
Closing.
Call eval in recursion without the starting and stop parentheses, obviously, because otherwise infinite recursion. And take this as the value to apply to the accumulator. So at this point, with this value from the recursive call, again, you do accumulator equal operation apply left and right. Right will be, in our case, the result of the recursive call. right?
Exactly, yes.
Okay. So, okay, you can copy line 36 at this point.
Actually, you gave me a good idea. I'll call this one right and right. So it's consistent with the naming we are using.
Yeah.
Okay, so...
Okay, search for the matching closing parenthesis.
So the way that I described before is basically let open, I guess, equal 1, because we already found 1. And this is mutable because we might increase that. And at this point, we need to keep...
consuming the expr.
Exactly. So we could do something like this, and then maybe we break. Makes sense? So we could do something like this, and we could break.
Yeah, or find the end of the string or break. But if you find the end of the string, it means that there is no closing parenthesis for this open parenthesis, and that is a bad input. So let's go with this, just to be safe. It will never happen that we...
So we're going to clone the input then? Because we don't want to consume it, right?
Yeah, but it's not a problem. When we take a character, we put in the string that we are passing to eval.
We'll need to build a string.
Yeah, we have to build the string to pass to eval or not.
Okay, now I remember why that approach where we have the indices gives us a little bit more flexibility, because then you can just keep reference of the I you had until here in the outer loop. And then here, when you find the J, let's call it J, the ending point, you just say evaluate from I to J of this current string.
Give me a substring and it's easy peasy, yeah. So right now we need to create a new string, or
do we want to use this other approach? With indices, yeah.
We can start creating the string, then we can do a secondary factor when we have test working, probably.
So let mute S, I guess.
Just call it substring.
Sub-expression.
Sub-expression.
Expression. And that is a string from nothing initially, I guess.
Yeah.
Okay, and now what do we do?
Now we take a character from the expr with the pop front and wrap.
So we copy all of this.
Line 33.
And now if C
is an open bracket, we do open
then
plus
basically 1. Open plus equal 1.
If it is a closed bracket,
C is equal a closed bracket, we do open minus equal 1, and here if open is equal to 0, then we found the matching parenthesis.
And our right is equal to eval of our subexpression.
Exactly. So here what we do is
right equal to eval of our subexpression. Then we have
I forgot.
No, we have to do that.
We also need to push.
I think everything else we need to push it to.
Even the open bracket.
Even open you gotta push.
Not the close,
but not the first ones.
Sorry?
I mean, we don't have to push it the first time and the last time, otherwise we'll recurse infinitely.
No.
Right?
The first one is already consumed by the loop above you in line 39. Yeah. It's already gone, the opening one.
We're doing that pop front on 44, which is basically taking us to the next.
The only moment that we don't have to add the character to the output string is when we do the call. It's inside that if. Else, everything else must be added to subexpression. So you can add the subexpression there, and then we have to remember to call without the last character if we are in line 51.
Push.
How do we add it to a string?
A char, nice. You can just push a char. So push C, I guess.
Okay. In line 51, we have to do right equal to eval of subexpression except the last character, because
so let right equal
probably the let
eval
is to do above
of sub expression. Basically we want to do from 0 to Does it work if you do -1?
Except the last character. I have no idea how to do that. Can't you just pop the last character before calling eval?
Let's see that.
Sub-exp
dot pop. Maybe. What does it do? Does it remove the last one? Removes the last character. Perfect. So then what we can do is just that, and we pass it with an ampersand. And I think that will do a casting to an str, from a string to an str.
Okay.
And now what we want to do... Go ahead.
I was going to ask, where do we stop this loop?
Here. We break here.
We will break here, yeah.
Cool.
And now accumulator is equal line... Basically, you copy line 36.
Exactly, yeah, this one.
Then probably this can be refactored, but let's have a working solution. Then we can refactor as long as we want. Okay.
So here we are calling recursively. Let me put
take the result and apply it.
And I think that's it, right? Because since here we are consuming, we keep consuming.
Yeah.
Basically, when we go outside this inner loop and we come back to the main loop, we already consumed all the parentheses, all the stuff in parentheses.
And if there is a space, we don't care, and we don't take spaces in account. It will do nothing with spaces. So if we do a match, if we convert that to a match, we have to remember to use the underline to match the space and just do nothing.
Let's see if this works. So this will be without all parentheses, right? This is literally
real life math.
So if this works, that there is reasonable trust that our implementation is correct.
If you disappear, cool. It's not an infinite loop. I was going to say, if you log off, it was infinite.
Let's do +2.
At this point, you have to put parentheses there. No, because...
And we can put parentheses here, but doesn't make a lot of difference, right?
Well, it makes, because plus you have to do that.
Oh, yeah, we'll need to do it here as well.
Yeah, exactly. Yeah.
Cool. So let's try that. Okay, still works. So our solution is probably reliable.
So we can run the
actual test. We can implement part 1 and then...
now it becomes trivial here, right? Because it's literally input dot lines dot map, yes. And map is going to be L eval of L.
You can't just pass eval without...
I think you can just pass eval. I'm curious to see if it's going to suggest us to do that. And then sum.
Yeah.
That's it.
Cool.
Is it going to suggest us to do that?
Nope.
No, but I think we can do it.
Let's see.
Yeah, that works. I don't know. Clippy sometimes suggests you that to do that. Let's see the solution. Does it work? Yeah, nice. It was even quite fast.
Now we have to do the optimization that you were suggesting. Do you want to add a benchmark now? Well, probably we already have them. I see a benches folder there.
Oh, yeah. Did we add them already? We did.
I might have done it. I'm not sure if I did it for this or the last.
Good job, Eugen, if you did.
Cool. Go on the terminal and try in the folder and try a cargo bench in the folder. Otherwise, it will trigger all the cargo bench.
So we do, now that I know the shortcut. Do I know the shortcut? I do. So CD year 2020, exercise 18, and we do cargo bench.
Obviously, the benchmark of part 2 is fake because it's just part 2 is fake. But part 1 is there.
Does it run the test? I never realized.
It compiles it, but I don't think it runs it. I don't know why. Don't ask me. Okay. Part 2 is very, very fast because it's retarding an integer. Part 2 at the moment is cheating. Part
of course.
Is working. Now, if we do a refactor, we can run cargo bench again and see if our refactor make it faster or slower.
Yes, and
because
the refactoring...
cargo bench is saving in the target folder the run.
Yeah, the results.
The results.
A refactor we can do is the one where we...
The one you were talking about indices, so you don't
we don't use sub-expression, basically.
We don't have to create that string because we keep track of indices and we slice the input string. But at that point, we have to move on top of S with an index that, as we saw in Rust, is not possible. So we have to do something.
I'm sure
so
it is.
Basically, I was thinking items. I'm going to call it items. And this is going to be sides and char. And basically, rather than doing chars, we do chars indices and collect. Now, at this point,
it's okay. It's giving you back a tuple with position and char. Okay.
So at this point, C is this will give us I and C, right? I and C.
And it's no longer EXPR.
And it's not expression, but it's items. And now pretty much everything else stays the same, but here we know that I is the starting point. So we don't need this anymore.
We just have to set.
And save, this is going to be... We can still do this.
Did you commit before? No.
I didn't.
It would have been cool to have the two versions in Git history if you want to check.
Ctrl-Z like crazy.
Sorry for only saying this now, but I guess better late than never.
You can do Ctrl-Shift-Z, that is redo.
Done, right? Cool.
Save.
So let's git status.
Can you run the
test? Just to be sure I didn't break anything. Okay. So first solution for year 2020, exercise 18, part 1.
Well, you could have pushed it later, but well.
Very good idea, Eugen. Okay, so now we can do Command Shift Z and
a bunch of time. We go forward in time. Okay. Now again, there it is
items, and now it's J and C.
Yeah.
Right.
Yeah.
And now we don't need to do this.
We don't need to push. We just have.
We don't need to pop.
No.
What we need to do is expression from I.
No, is S. Sorry, is S your input value?
Right, you're right. S.
Okay. From -1 to J.
Guys, we're still popping on 43. Pop front dot unwrap.
Oh yeah, no, we need to do this to still consume the items, which is like the indexed view.
Yeah, correct. Sorry. It's.
And I think that's it.
If we are fine with the off by 1 error of indexes.
I think we need. This is not going to be inclusive.
Okay,
so we are saying skip the first one.
Okay.
Go until the closing parenthesis, but that closing parenthesis is excluded.
But well,
let's see if I got it right.
Let's run the test and let's run the bench.
So let's run this one first. Still working. This one.
Did it?
Still working, right?
I don't know. I can't see the hole.
Let me make it bigger. Okay, let's close this and let's do cargo test. So it runs everything. Okay, cargo bench. Now this is gonna do like a diff if there was an improvement, right?
Yeah, it gives you a percentage plus minus. Ignored.
No,
this is just the test.
The tests are ignored because cargo bench is not. You can run the test with cargo bench, but why? Yeah. Oh, it's even faster. But obviously, because we are not allocating the string, so it's faster.
Yeah. It's 30% faster, even almost.
Yeah, around 30% faster. Yes,
which is great.
Well, part 2, don't read part 2 for now. It's fake.
Part 2 is.
So cool. This is faster. Do we want to also do a comment? Good. Do we want also to use a match instead of an if, else if?
Sure. Let's try.
We could try that. Let me do a comment here.
Yeah, do a comment here that we have a working solution with improved
performance by
not allocating,
but not allocating.
Yeah.
Sub exp. Okay. Pretty cool. So we wanted to use a match here.
I don't know. Can we?
I don't know if we can do this, like a contains.
We can try.
Maybe, yes. Okay, let's see. So let's see. So we can do match C. And then the first thing I think is if we just do this, that will mean equal. None.
Okay.
I think that will be equivalent to what we just said. So that will be the first thingy. And we need to copy this. Then the other case is
star or
asterisk or
plus
as a string, and the or should work there. I don't know if we need maybe just one pipe, probably. Yes. And now this is it. Now the last case is parenthesis. Open parenthesis. Okay. That should be all of that until here. Save it. And now it should complain because this is not extensively, right? Why it doesn't complain?
Yeah, up there in
Oh,
C.
there is an error here, non-exhaustive pattern. Okay, there it is. Because we need to say underscore and say that this is in theory reachable.
No, we have spaces. That is reachable.
Oh yeah, we ignore like.
We just ignore, but that is reachable.
Other character, fair enough. Like if we use that reachable, it will panic as soon as
it will panic. So no, thank you. Yeah.
And we need a comma there, I guess. Oh no, you don't need commas because we have
need commas between brackets. Okay.
Cool.
So we could do the same here, I guess.
But we have two cases there.
Let's run the tests just to make sure. Run the eval test, the small one, to see if we...
Let's run all the tests. Why did it disappear? Tell me. Cargo test. Yeah, still works.
Cool, we're good. Yeah, let's do this one as well.
So much C, and we have parentheses basically. Okay, here we can just do this, I guess.
Because we have just one command.
And then you need the other one is this, and you need a comma, yeah. And now here we have all this stuff, basically.
Yep.
And the underline.
And then we need here underline, which again is going to ignore every other character.
And I think you need to de-indent all this stuff. To indent.
Why it's complaining? I think here we either I think I have no. Do I have an additional?
Do you need a semicolon on line 62?
I think here we need. Yeah, okay. I was missing a closing curly bracket.
Okay, so.
Is this more readable? Maybe.
Yes.
Yeah, it is.
Yes, in my opinion, it is.
Okay.
Very important, so that specificity on the comment.
Yeah, let's run the tests again. Cargo test. Sounds
and I'm
good.
Very curious of the bench now. I don't think it makes any
difference. let's run the bench.
I don't know if matching is faster than if. Let's see.
It could be fast.
Because the algorithm is exactly the same, so it's just a matter of 1% is not.
It's probably
I don't know. It's not noise. It's not exactly noise because you're not in the cloud. You are on an hardware machine, but okay, it's slightly faster, but nothing incredible.
Okay, so git commit am using much rather than
if
a bunch of if else like crazy.
Correct.
What do you mean, Tommaso, with p-value? I'm not sure I'm following. You mean that this could be just noise in the rounding?
Go back to the numbers. I missed above. No, it's part 2 that is 0.6 more than 0.5. It's part 2 is just fake for now.
Yeah. Oh, okay. This is the
one for part 1 is that one.
What does this one mean, by the way?
If your test is noise, if the test is noise or not, if the change is just noise or not.
And how do you tell if it's noise?
I think based on the value.
Like this one should be noise, right?
That one is noise because P is evaluating to true, and the other one is not noise because the first one.
Okay, so if this is true or false, you can tell whether it's noise.
I'm not sure. For the second one is for the part 2 is noise for sure because part 2 is returning an integer. So
actually, Tommaso is giving us a link, which I think is good to put here, and probably we're gonna add also in the description on YouTube.
Okay, we can take a read to get a better idea of what it is. So basically,
thank you, Tommaso.
It's a changes within noise threshold. Yeah, well.
And this one says no change detected because that difference is noise. Cool. Yeah, that makes sense.
Next time that you run it when we do the implementation, it will be crazy slower because it's doing actually something.
Fair.
Okay, so I think we are at about 1 hour, like in 2 minutes. So I'd suggest we stop here for today.
Right.
Any final remark before we do the closing?
Just this was an interesting one.
Yes. There is also another way of solving this with reverse Polish notation, but it's slightly more complicated to explain. So, and also here we don't have multi-figures numbers, stuff like that. Our input is simplified.
Yeah, I think if we add multiple digits numbers, we'll need to either create a more complicated state machine where you have like started a number, completed a number.
Yeah, but at that point it gets complicated. So at that point it's better to have a tokenizer that is tokenizing the input and then work with a state machine on the tokens.
Exactly.
So you split the job in tokenize and parsing.
I would love it if we could do the other solution to this problem at some point. Maybe not next time because we should do part 2, I guess. But I think it would be cool to do the stack approach. It'd be interesting because it's not a usual solution that you see or hear people use.
But I think it's the more traditional solution, right? I think it's the solution that calculators implement. The Polish reverse Polish notation.
Well, reverse Polish notation was used in HP calculators. There was a movement that was the not equal movement. So the logo was unequal with a slash. So a not equal. And basically we're saying, no, our calculator doesn't have the equal on the calculator because you just do numbers and operation. When you click the operation, you have on the display the result based on what you have on the stack. So you had pushing the stack, pop from the stack, and operations. So only electronic engineer can think of something like that.
Yeah, the reason I said
the calculator were cheaper because it was more, it was easier to build. It was just a stack and some logic to do operation on the stack based on what button you were pressing. So the electronics was way cheaper.
An anonymous cheerer just cheered 1 bit. I'm not super certain what that means, but it just happened and I wanted to point it out.
And thank you for doing that.
I have no idea what 1 bit is in Twitch context.
Thank you.
We'll probably spend some time to figure that out.
We'll find out by next time. All right. Should we wrap it up then?
Yes. Meanwhile, I'm going to search for somebody to raid, but I'll let you do the closing.
Coolio. All right. So, well, for everybody who joined or maybe joined a bit late and so on, you can find the recording on YouTube. If you're watching this on YouTube, well, we stream this every Monday on Twitch. The link for the YouTube channel will be in Twitch in the About section, and the link for the Twitch channel is in YouTube. Should be there. Now, live streaming happens every Monday, 5 p.m. UTC, which is currently 6 p.m. because summertime. So make sure that you check the Twitch link in YouTube and give us a follow so you can be notified when we put these out. Feel free to leave us comments or open pull requests. Like we said at the start, this is all on GitHub, so it's open source. It's free for anyone to contribute. The repository of the codes, did you put a banner, Luciano?
Wait a sec.
Waiting.
There you go.
Super smooth. There we go. You can see us on github.com. Right. So any contributions that you have are well accepted. Thank you. We're trying to learn, so don't expect our code to be the most amazing or the most bestest solution out there. But do contribute. We try to improve things. We accept PRs. We've shown a few in the past. So thank you all for the suggestions today and for the collaboration. And we're going to rate someone. Thank you very much, and see you next Monday.
Bye.
Bye.
Bye.